Good morning, good afternoon, or good evening, whatever the case may be. This video is Section 1, Chapter 1, a preview of calculus. It's a short section and a couple bullet points here. We're going to understand what calculus is and how it compares to pre-calc. Understand that the tangent line problem is basic to calculus, and also the area problem is basic to calculus. Calculus grew out of these two concepts. What is the slope occurring at a single point on a curve, and what is the area under a curve. So both of these were explored independently, and at some point they figured out that these were opposite sides of the same coin. And what ties them together is the fundamental theorem of calculus. But that's a long ways away. For some reading here, it says, what is calculus? Calculus is the mathematics of change. For instance, calculus is the mathematics of velocities, accelerations, tangent lines, slopes, areas, volumes, arc lengths, centroids, curvatures, and a variety of other concepts that have enabled scientists, engineers, and economists to model real-life situations. That's a big use of math. You look at some data, you come up with a model of something going on in the real world, and you can use that model to predict the future or maybe figure out stuff from the past. And it goes on, although pre-calculus mathematics also deals with velocities, accelerations, tangent lines, slopes, and so on, there's a fundamental difference between pre-calc and calculus. Pre-calculus math is more static, it's unchanging, where calculus is more dynamic. And here's the book provides a few examples. An object traveling at a constant velocity can be analyzed with pre-calc. Like if you're on an interstate doing exactly 60 miles an hour and that does not change, you have constant velocity, and you can get away with using simpler pre-calc math. To analyze the velocity of an accelerating object, you would need to use calculus. Think about the space shuttle launching. As it launches, it's picking up speed, it's accelerating. The mathematics behind getting a rocket into orbit is not pre-calc math. You'd have to use calculus. Second one, the slope of a line can be analyzed with pre-calc math. The slope of a line, it's just 2 points, point 1 and point 2, connect them with a straight line. The slope of the line is constant. To analyze the variable curvature of a back up here, to analyze the slope of a curve, not a straight line, we would have to use calculus. Third one, the curvature of a circle is constant. We can analyze a circle's curvature with pre-calc. To analyze the variable curvature of just some general curve, we would have to use calculus. And finally, the area of a rectangle can be analyzed with pre-calc. Rectangle, that's just length times width. To analyze the area under a general curve, a non-rectangular shape, we would have to use calculus. Each of these situations involves the same general strategy, the reformulation of pre-calculus mathematics through the use of a limit process. So one way to answer what is calculus is to say that calculus is a limit machine that involves three stages. First stage is pre-calculus math, such as the simple slope of a line or area of a rectangle. The second stage is this limiting process. And the third stage is our new calculus formulation, such as what you'll come to know as a derivative or an integral. So we take our pre-calc math that we've already figured out, we apply this limit process, and that leads us to beautiful calculus. And some students try to learn calc if it's just simply a collection of new formulas, and that's unfortunate. If you reduce calculus to memorization of differentiation and integration formulas, you're going to miss a great deal of understanding, self-confidence, and satisfaction. On the next 2 pages are listed some familiar pre-calc concepts coupled with their calculus counterparts. Throughout the text, your goal should be to learn how pre-calc formulas and techniques are used as building blocks to produce the more general calculus formulas and techniques. Don't worry if you're unfamiliar with some of the old formulas listed on the next 2 pages. We'll be reviewing all of them. As we proceed through the text, come back to this discussion repeatedly. Try to keep track of where you are relative to the 3 stages involved in this study of calculus. For instance, note how these chapters relate to the 3 stages. So here we go. Here's our examples. On the left is pre-calc stuff, and on the right with calculus. So in pre-calc, we could find the value of a function at a given x value. We would plug in that x value, find its height on the y-axis. That would be our function value. But what about the limit as we approach? What if our graph has a hole in it and we cannot directly evaluate c? How would we figure out what that y value is going to be? We would use calculus, find the limit as we approach. In pre-calc, slope of a line, easy, a line is straight. It has a constant slope all across the line. But what if we want to find the slope at a curve? The slope down here is going to be different from the slope here. Every time we move along the curve, the slope is changing. To find that slope anywhere, anytime, we would have to use calculus. Third one, secant to a curve. Pick 2 points on the curve, and the secant line will cut through it. That's no problem. But what if we want the tangent line at a single point? Here's a point of tangency, and we want that tangent line to hit it. Pre-calc, an average rate of change. We could find the beginning point and the ending point and find the average across that time interval. But the beauty of calculus, we can find instantaneous rates of change. How fast is it changing at that one moment in time? Pre-calc, we can find the curvature of a circle because the curvature is constant. But with a general curve, that curvature is changing. Just as it has different slopes at each point, it has different curvature. Pre-calc, the height of a curve at a certain point. With calc, we'll be able to find the maximum height of a curve on an interval. Especially for if you're working in business, cost curves or production curves. You want to maximize profit or minimize costs, and we would use calculus to figure those out. Pre-calc, tangent, a plane tangent to a sphere. So we have a sphere, we can find a plane that is tangent to it. But with calc, we can expand that to find a plane tangent to any given surface. That would be more calc 3. We won't be doing any of that here in calc 1. And the last one down here, direction of a motion along a line. To calcify that up, the direction of a motion along a curve. Because again, as the curve progresses, those directions of motion will constantly be changing. Calculus is all about accounting for the change that we see in the real world. Here's some more. Without calc, we can find the area of a rectangle, no problem. Little geometry formula, and we're good to go. But with calculus, we want to find the area under a curve. And it's not going to be a simple rectangle. In pre-calc, we could do work done by a constant force. If we're constantly pushing on that and the force with which we're pushing does not change, we can get by with pre-calc. But if the amount of work we're doing is a variable force, if it's changing as time goes by, we would have to use calculus. Pre-calc, we could find the center of a rectangle. We could use calc to find the centroid of any region, not just a rectangle. Pre-calc or geometry, we could find the length of a line segment. But what if that's all curvy? What if we wanted to sort of straighten that out and measure it? Well, we could use calculus instead. Geometry or pre-calc, the surface area of a simple cylinder. But what if it's not a simple cylinder? What if we have this, it's got curves on the edge, a solid of revolution? What if we want the surface area of that? We'd have to use calculus. Pre-calc, we could find the mass of a solid with constant density. But what if it's variable density, like the Earth? As you go through the Earth, different densities of the crust and whatnot, we'd have to use some sort of calculus formula. Pre-calc, we could find volume as long as the shape is something simple like a sphere or a rectangular prism. But in calc, as long as we have the equation, we can figure out any volume or region that we want. Now, back here, we're going to talk the tangent line problem. This is sort of one side to the calculus coin. And the book goes on to say, the notion of a limit is fundamental to the study of calculus. The following brief descriptions of 2 classic problems in calculus, the tangent line problem and the area problem, should give an idea of the way limits are going to be used. In the tangent line problem, we're given a function f and a point P on the graph of that function, and we're asked to find the equation of the tangent line to the graph at that point. So here is our y equals f of x, that's this curve. We are given point P here, and we want to find the tangent line at that point of tangency. Once we have that slope, we could use that to find the equation of the tangent line. The thing is, usually to find the slope of a line, we're given 2 points. You might remember good old y2 minus y1 over x2 minus x1 to find the slope. But to use this slope formula, we need 2 points. In calc, we just want the slope occurring at that 1 point. How can we find the slope at a single point? Well, we use this limit process. And it says here, except for cases involving a vertical tangent line straight up and down, the problem of finding a tangent line at point P is equivalent to finding the slope of the tangent line at that same point. If I back up to the picture, this blue tangent line here, we could find that slope if we knew a couple points on it. The slope of this tangent line is also the exact slope occurring at point P at that point of tangency. If we move up here and make this point P sub 2, the tangent line would be much steeper, the slope would be different. And where did I leave off? Blah, 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 blah. You can approximate the slope by using a line through the point of tangency and a second point on the curve, as shown in the figure. We'll get to that in a minute. Such line is called a secant line. Now, before we get too deep into this, let me go through this. This might make things a little clearer. On the couple slides ago, I did refresh your memory of y2 minus y1 over x2 minus x1. That is the slope between 2 points. Like, let's say I pick a point here, and I'm going to call this x sub 1. X sub 1 goes in, and it gives us this y value, y sub 1. If I pick another point over here, this would be our input x sub 2, and we'd find that on the curve and follow it over to the y-axis, and that would be our y sub 2. Remember, rise over run. So to get from the red point to the blue point, I would first rise up this distance between y2 and y1. That's why they're subtracted here in the numerator. And then I would run over to the right the distance here from x sub 1 to x sub 2. So here's how we found slope before calculus. Now let's calc this up a little bit. And I'm going to use a slightly different notation. Did they use C's and X's? Yeah. So let's call this point first here, point C. And then it would hit this point, and this would be our output f of C. So we have our first point right here. Now, just to keep this real general, instead of just picking any point out here, let's just say we're going to start at point C and jump over some amount, and we're going to pull out the Greek alphabet here, that is delta x. So we're at point C, and we're going to move along the x-axis some amount, some delta x. And we're going to call this point C plus delta x. And that might take us up to a point. I'll put it right about here. It really doesn't matter. And we take that over to the y-axis. Here, our output, when we put in C, we got f of C. So this is C plus a little bit more. This is going to be f of C plus that little bit more, that little delta x that we moved along the x-axis. So here is the same concept, but with some slightly different notation. Now, if I take, let me start a new slide here, y2 minus y1 over x2 minus x1. Well, let's just use the new notation here. Y sub 2 minus y sub 1. The higher y value minus the lower. So this is going to be f of C plus delta x minus f of C. So we took this from pre-calc, that's our movement along the y-axis, and we've rewritten it here with some new calculus notation. Let's see what's going on down in the denominator. So our denominator is x sub 2 minus x sub 1. Well, here's x sub 2, C plus delta x, and then we're going to minus x sub 1. So down here, C plus delta x, and then we're going to minus x sub 1. Now, there's nothing we can do here in the numerator. Those are distinct terms. But here we've got a C minus a C. So those are going to cancel out. So what we're left with here is f of c plus delta x minus f of c. That's our numerator, or our movement along the y-axis. And then down here, after the c's cancel, we're just left with delta x, our movement along the x-axis. So this is our calcified way to talk about slope. So back to the slide here I sort of gave up on. It says here, second point, blah, blah, blah. Those two slopes, the slope between the points can be found using pre-calculus and is. Here's where I had that. F of c plus delta x minus f of c over c plus delta x minus c. So the c's cancel, and we're left with this. F of c plus delta x minus the original f of c all over delta x. Let me back up here to this for a minute. Now, what's the idea of the limit process? What we want to do, the closer these 2 points are to each other, the better our estimate's going to become. So what we want to do is sort of move closer, and that will maybe move this dot a little bit closer here, and we'll move closer. And this will get us closer to this point. And the idea is, how close can you get without actually getting to point C? Like, here's a number line. I'm just going to pick a number 5. How close can we get to 5 without actually getting to 5? Well, I might call on one student, and they might say 4.9. That's pretty close to 5. Another student might say, well, 4.99 is even closer. And then somebody else might say, well, 4.999 is even closer to 5. And you see where we're going here. We could just keep doing that to infinity. 4.9999999 is real close to 5. So how close can we get to 5 without getting there? We can get infinitely close. We can get so close to 5, it's like finding the slope using the same point twice, if that makes sense. So this idea of a limit process, we want 2 points to find the slope between, but we don't want to move too far along the x-axis. We want to keep these points as close as possible. And how close can we get them? With calculus, we can get infinitely close. And when we do that, our estimate of the slope is no longer an estimate. It becomes the actual value. So let's see what we got here in the book. Here's the stuff I wrote out. You know, they move along here delta x amount, and then that moves us up higher. And here's the idea of moving the points closer. Here's point P. We want the slope at point P. It's not going to move, but we could pick a point Q out here and get an estimated secant line slope. And then we could move it closer for a better estimate, and even closer still, and closer still. The idea is to get infinitely close. And the book says, as point Q, that's up here, approaches that point P, the slope of the secant line approaches the slope of the true tangent line. When such a limiting position exists, the slope of the tangent line is said to be the limit of the slopes of those secant lines. We'll see more about that in the next chapter. So that's the first half, or first side of the calculus coin. The other side is not about slopes, it's about areas. And it says, in the tangent line problem, we saw how the limit process can be applied to the slope of a line to find the slope of a general curve. A second classic problem in calculus is finding the area of a plane region bounded by the graph of functions. This problem can also be solved with the limit process. In this case, the limit process is applied to the area of a rectangle that we use to find the general region's area. As a simple example, consider the region bounded by a function, the x-axis, and a couple vertical lines. We'll see that in the figure on the next slide. We can approximate the area of this region with several rectangular regions. As we increase the number of rectangles, our approximation becomes better and better, because the area missed by the rectangle decreases. The goal is to determine the limit of the sum of the areas of these rectangles. Let me just start here on the picture. We've got a shape. We want to find the area of it, and it's not a simple geometry problem. Here's our function f of x, and we're going to go above the x-axis. Between this line, A, and B, this pink shaded region, we want to find the exact area of. So many years ago, our mathematical forefather said, well, I can't find the exact area, but I can come up with a good approximation. Between the endpoints A and B, I'm going to chop that up into 4 rectangles, 1, 2, 3, 4. I can use these x values to find the height of these rectangles. And once I've got the height of the rectangles and I know the base, I can use length times width. So here I would do the length and the width of rectangle 1 plus the length and the width of rectangle 2, the length and the width of 3 and 4. And I would add up those 4 areas to get my estimate of under the curve. And then somebody said, well, if I can get a decent estimate with 4 rectangles, what if I chop each of those rectangles in half again? And now I'm up to 8 rectangles. Notice here in the first one, we had some area that we missed. This region here was not counted, as was this. When we reduce or when we increase the number of rectangles, that little bit of area has now been lessened. That error has now shrunk and our estimates become better. So here we went from 4 rectangles to 8 rectangles. We could do it again and bust those each in half and make 16 rectangles. And then do it again and get 32 and 64. The idea here with the limiting processes in this, let's say we started at 0 and we went to 4, each rectangle had a base of 1. And then when we chopped them in half again, each base went to 1/2. As we cut these rectangles in half again and again and again, the bases become less, and we double the number of rectangles. As we apply the limit process, we're going to theoretically break this area up under the curve into infinitely many rectangles. Each rectangle is infinitely thin, and then we're going to add up all those areas. And if it sounds difficult, it's actually not. Again, we're going to make infinitely many rectangles, use the length times width formula, find the area of each rectangle, and add them up. Ooh, and I guess that is the end of this slideshow. To go over some of this stuff, I have some activities planned for class. We're going to do some of the book calls them explorations. We'll get out the TI-89 calculators, and we'll work through some of these, get an idea of the nuts and bolts, what's going on before we get to the good shortcuts and all that stuff.